The concrete designed for our highways, bridges, and other structures is intended to be of the highest quality. It should consist of approved materials that are correctly proportioned and mixed, and then carefully transported to the job and placed. In practice, however, the concrete ordered for the job may not be the concrete that's actually placed. At critical points during production, transport, or handling on site, the concrete's quality may be jeopardized. Batcher mixer slips are not always a guarantee that you have the right concrete in the truck. For example, if wash water was left in the truck before it was loaded, the mix may be too wet. Or the truck driver may decide to add water if the mix begins to stiffen. So it's important and it's required that the quality of the concrete be verified before the concrete is cast. Verification is provided by conventional controlled tests performed in the field. This presentation is the first of 4 videotapes on quality control of concrete on site. Here in Part 1 and in Part 2 are presented the conventional control tests for determining concrete quality at the job site. In Parts 3 and 4, you'll see new quality control procedures that have been developed by Sharp and others for testing concrete both before and after it's cast. So, here in Part 1, we'll look at sampling concrete and at the test methods for temperature and slump. In Part 2, we'll look at the test methods for air content and unit weight, as well as the procedures for making cylinders and beams. Our first topic then is sampling. Before any of the tests can be performed, a sample of the concrete is needed, a representative sample. The concrete to be tested has to be typical of the entire truckload. Sampling should be done according to AASHTO designation T141. The basic rule is this: don't take the sample from the beginning or end of the discharge. Take it from the first 1/3 of the discharge, but never from the first 2 cubic feet. To obtain the sample, either the entire stream should be caught in a container, or the chute should be swung over to the side. The important point is to get the entire stream. Cutting the stream in half, like this, is unacceptable. The rim of the bucket will knock some of the large aggregate out of the sample. The sample should be mixed with a shovel just until it has a uniform appearance. Then it should be covered to protect it from the sun and the wind. Samples must not be allowed to dry out. One last point. Testing must be completed within 15 minutes after obtaining the sample. Now, temperature. The temperature of fresh concrete affects the rate at which concrete gains strength, the amount of strength the concrete ultimately acquires, and the porosity of the concrete. Checking concrete temperature is simple. It should be done according to ASTM C1064. All that's needed is a standard thermometer, such as an ASTM liquid in glass type, or a metal immersion type. The thermometer is inserted into the fresh sample so that the temperature sensing portion is submerged at least 3 inches. The concrete should be gently pressed around the thermometer so that the air temperature does not affect the reading. The thermometer is left in the concrete for 2 minutes or until the temperature stabilizes. Then the temperature is recorded. The measurement must be completed within 5 minutes after the sample is obtained. The temperature of in-place concrete is measured in the same way. Now, the air temperatures during concrete construction are also important. The high and low air temperatures must be monitored daily. Next on the list is the slump test, AASHTO T119. This is by far the oldest and most widely used test to measure the uniformity and consistency of concrete. Variations in slump generally indicate that changes have occurred in the properties or proportions of cement, aggregates, water, or admixtures. The equipment needed for slump tests includes a standard slump cone, a standard tamping rod, a scoop, a base, and a ruler or measuring tape. The slump cone should be reasonably clean, especially inside. The surfaces should be smooth, with no dried concrete on them. Also, there should be no major dents. A standard tamping rod is smooth with a rounded tip. Makeshift rods, such as cut-off reinforcing bar, are unacceptable. The base for the cone must be strong, rigid, and stable enough to support the tester as well as the concrete and equipment. It needs to be level and firmly supported so that it won't rock or bounce. The sample should be brought close to the test location and remixed if necessary until it looks uniform. The test is begun by first dampening the inside of the slump cone to keep the concrete from sticking to it. Then the base is dampened as well, so that it won't absorb water from the concrete. But no freestanding water should be left on the base. The cone should be set down on the base as close as possible to the sample. Next, the technician steps onto the footholds at the bottom of the cone and stays there. That's why the sample and cone need to be close to each other. The cone is filled by moving the scoop around the top to distribute the concrete as evenly as possible. The filling is done in 3 layers. Each layer should take up approximately 1/3 of the cone's volume. So the first layer should come up about 2.5 inches from the base. The second layer should come up about 6 inches. That's about halfway up the cone. And the third layer should overflow the cone. As each layer is placed in the cone, it's consolidated with a tamping rod. Starting at the perimeter, with its rounded tip downward, the rod is inclined slightly to match the slope of the cone. Otherwise, the concrete closest to the cone's sides will not be properly consolidated. The rodding should go to the bottom of this first layer, but just tap the base. Each layer is rodded 25 times, with about half of the strokes made near the perimeter. A spiraling pattern should be followed as the rod moves toward the center of the cone. The strokes are distributed uniformly. As the rod is moved away from the perimeter, it's returned to the vertical. The second layer fills about half of the cone's height. It's rotted the same as the first, with one difference. The rotting should just penetrate about a ½ inch into the first layer, not all the way down to the base. The third layer should overflow the cone. That way, the concrete stays above the cone throughout the rotting. If it drops below the top, the rotting should be stopped. More concrete should be added, and then the 25 spiraling strokes should be completed. And the rod should just penetrate the top of the second layer about 1/2 inch. With the cone full and the rotting completed, the surface of the concrete is struck off by moving the tamping rod across it in a screeding and rolling motion. The concrete surface must be level and fairly smooth. Next, any concrete that has spilled around the bottom of the cone must be removed. Otherwise, it may keep the sample from slumping properly when the cone is lifted off. However, the technician must be careful not to move the cone and disturb the concrete. Basically, both sides of the cone must be held still by pressure on either the handholds or footholds until the cone is removed. To remove the cone, both hands are placed on the handholds and downward pressure is applied to keep the cone stable before the feet are removed from the footholds. Now the cone is pulled straight up, slowly and steadily, without twisting or tilting. The removal should be completed in about 5 seconds. Slowly enough that the concrete doesn't pull on the cone. The cone is then set on the base, next to the concrete, without touching the concrete or jarring the base. Immediately, the tamping rod is laid flat across the top of the cone, extending over the concrete. A ruler or measuring tape is used to measure the distance between the bottom of the rod and the top of the concrete. The measurement should be made to a point that is directly above the center of the bottom of the concrete, not at the center of the top. The entire slump test must be accomplished within 2 minutes, as measured between the adding of the first layer and the measuring of the slump. And that's sampling, temperature, and slump. And the end of part 1. In part 2, we'll cover air content, unit weight, and the making of cylinders and beams. This second part of quality control of concrete on site will examine the test methods for air content and unit weight, plus the procedures for making cylinders and beams for compressive and flexural strength tests. To begin, air content test methods. The results of air content tests indicate the freeze-thaw durability of concrete. Air-entrained concrete with the specified air content performs much better than non-air-entrained concrete in freezing and thawing conditions. On the job, concrete can be rejected if its air content is not within the allowed range. The most popular method for measuring air content is the pressure method. 2 types of pressure meters are available and are widely used. They are referred to as Type A and Type B, and are covered in AASHTO T152. With Type A air meters, the equipment needed includes a calibrated Type A meter, a tamping rod, just like the one used in the slump test, an internal vibrator, a rubber or rawhide mallet, a scoop, a strike-off bar, and a supply of fresh water. The meter consists of a measuring bowl having a capacity of at least 0.2 cubic foot, and a cover assembly that includes a standpipe, a pressure gauge, and an air pump. The cover assembly also contains a number of valves and petcocks. The bowl and cover must clamp together to form a pressure-tight seal. As with the slump test, all the equipment should be clean and in good condition. It should be assembled near the concrete sample. The test is begun by filling the measuring bowl with concrete in either 2 or 3 equal layers and consolidating each one. The number of layers depends on whether the consolidating is done by rodding or vibrating. And the method of consolidation depends on the result of the slump test just performed. If the slump is less than an inch, vibrating is required. If it's more than 3 inches, use the tamping rod. And if it's between 1 and 3 inches, either method can be used. When the tamping rod is used, the bowl is filled in 3 equal layers. Each layer is rodded 25 times, and the strokes are distributed evenly over the cross-section. The bottom layer should be rodded throughout its depth, but without forcibly striking the bottom of the bowl. After each layer is rodded, the sides of the bowl should be tapped sharply with the rubber mallet 10 to 15 times around the bowl's circumference. This will close any voids left in the concrete by the tamping rod and release any large entrapped air bubbles. In rodding the second and final layers, only enough force should be used to penetrate the surface of the previous layer about 1 inch. Then, the final layer of concrete is added without excessively overfilling the bowl. When the vibrator is used, the bowl should be filled in 2 layers of approximately equal volume. After the first layer is added, the vibrator is inserted 3 times at points evenly distributed over the cross-section. The vibrator must not touch or rest on the bottom or sides of the bowl, and the concrete should not be over-vibrated. Such practices segregate the aggregate and lose some of the intentionally entrained air. The final layer is added without excessively overfilling the bowl. Then, it's vibrated the same way the first layer was vibrated. Usually, the surface has been vibrated enough when it's relatively smooth and looks glazed. The surface should then be struck off by sliding the strike-off bar across the top flange or rim of the measuring bowl. Then, the contact surfaces are wiped clean, and the cover assembly is clamped firmly to the bowl. The lower petcock is closed. The upper petcock and funnel valve are opened. And water is added until it rises to about the halfway mark in the standpipe. The meter should be gently rotated and tapped with the mallet to remove any entrapped air that may remain. Next, water should be poured through the funnel valve until it stands at a level slightly above the arrow mark on the graduated scale. The funnel valve is then closed and the level is adjusted to the arrow mark by drawing off just enough water through the lower petcock. Next, the top petcock is closed and pressure is applied with the air pump until the gauge reaches the exact air pressure required. The required pressure is known from the calibration procedure. Now, the resulting water level is read, the bottom of the meniscus on the graduated scale. This value is the gross percentage of air entrained in the concrete, or H sub 1. Then the pressure is released, and the water level on the graduated scale is read. This value is the lag, or H sub 2. The air content of the concrete is the gross percentage, H sub 1, minus the lag, H sub 2, minus an aggregate correction factor, G. Determination of the aggregate correction factor using both meters is covered in T152. The Type B test requires a calibrated Type B meter as well as the same equipment needed for the Type A test. The first step is to fill the bowl with concrete, consolidate it, and strike it off, the same as for Type A. Then the flange is wiped clean and the cover is clamped on with both petcocks open. Water is then injected through one petcock until it comes out the other petcock. With both petcocks open and the air bleeder valve closed, air is pumped into the air chamber until the gauge hand is on the initial pressure line. To stabilize the gauge hand at initial pressure, air is pumped in or bled off as necessary, and the gauge is tapped lightly. Next, both petcocks are closed and the thumb lever is pressed down. This releases the air into the bowl. The sides of the bowl are tapped sharply with the mallet, and the gauge is tapped gently with the fingers until the dial hand stabilizes. This is the gross air content percent. From it, the aggregate correction factor is subtracted. The result is the net air content percentage of the concrete. Now it's time for the unit weight measurement of fresh concrete. The unit weight, or density, is determined simply by weighing a known volume of the concrete according to AASHTO T121. The same equipment used for air content testing is needed, as well as a measuring container, or measure, a balance or scale, and a strike-off plate. The balance or scale must be accurate to within 0.3% of the test load. The measure must be a watertight cylindrical container whose capacity depends on the size of aggregate used in the concrete. For 1-inch maximum size aggregate, a measure with a minimum capacity of 0.2 cubic foot should be used. If the aggregate has a maximum size of 1.5 inches, the measure's minimum capacity should be 0.4 cubic foot. And for 2-inch maximum size aggregate, the minimum capacity should be 0.5 cubic foot. Since the air content meter's bowl has a capacity of 0.2 cubic foot, it can be used as the measure when the concrete contains 1-inch maximum size aggregate, as is becoming more common in pavements and bridges. The first thing to do is place the empty bowl and strike-off plate on the scale or balance and record the weight. The bowl is then filled in 3 equal layers of concrete, with each layer properly consolidated. Consolidation requirements are the same as for the air content test. If the slump is less than 1 inch, you vibrate. If it's more than 3 inches, you rod. And if it's in between, you have the option. The concrete surface is struck off and finished using the strike-off plate. The bowl must be exactly level full. Then all excess concrete is cleaned off the outside of the bowl, and the filled bowl and strike-off plate are placed on the scale or balance. The net weight of the concrete is determined by subtracting the empty weight of the bowl from its filled weight. To calculate the unit weight, the net weight of the concrete is divided by the calibrated volume of the bowl. The last topic is the making of concrete cylinders and beams on site for subsequent compressive and flexural strength tests. Other than the molds, all needed equipment is available from the other tests we've covered. The sizes of molds are based on the concrete used and on specific project requirements. To begin, the proper molds must be on hand and clean. The concrete is placed in the mold using the scoop or trowel. Then, the tamping rod is used to distribute the concrete evenly across the full area of the mold before starting consolidation. The number of layers required to fill the mold depends on the mold size or depth. Table 1 of AASHTO T23 details the specific mold requirements. For common molds, such as cylinders with depths up to 12 inches, the concrete is placed in 3 equal layers for rotting and 2 equal layers for vibrating. For beams with depths between 6 and 8 inches, the concrete is placed in 2 equal layers for rotting and just 1 layer for vibrating. Selection of the consolidation procedure depends on the slump, just as it did for the air content and unit weight tests. Less than 1 inch, vibrate. More than 3, rod. In between, optional. When rodding is used, the number of strokes is usually 25 for the most common molds. Table 2 of AASHTO T23 gives the requirements for other molds. After each layer is consolidated, the outsides of the mold are tapped lightly 10 to 15 times to close any holes left by the rod or vibrator. When beams are made, the tapping of the mold should be followed by spading the concrete along the sides and ends with a trowel or other suitable tool. To finish the cylinders or beams, a small excess of concrete is added to the surface, but not more than 1/4 inch. Then the surface is struck off. Normally, a wood or magnesium float is used to finish the surface, but a steel trowel is used if specified. Immediately after they're finished, the mold should be covered to prevent evaporation. Polyethylene sheeting is usually used for this purpose. Alternatively, wet burlap may be used, covered by plastic. In this program, and in Part 1, you've seen the on-site procedures for sampling fresh concrete, testing it for temperature, slump, air content, and unit weight, and making cylinders and beams for compressive and flexural strength tests. In Parts 3 and 4, you'll see new concrete testing and monitoring procedures developed by Sharp and others. The careful following of proper sampling and testing methods greatly enhances the quality control of concrete on site. In Parts 1 and 2 of this series, we presented the conventional quality control tests traditionally used for highway concrete structures. Now, there are new quality control tests and techniques recently developed by Sharp and others that can serve as useful and reliable tools for quality control of concrete. In this third program, and in Part 4, you will see a selection of these tests, both the test procedures and their application to concrete highway construction. The tests fall within two categories: as-delivered concrete and as-placed concrete. In the as-delivered category, you will see water content measurement and thermal effects evaluation. The as-placed category will include maturity monitoring, temperature-matched curing, pulse velocity testing, and nuclear density testing. We'll cover the first three tests here in Part 3 and the rest in Part 4. So we'll begin with water content measurement. It's well known that water-to-cement ratio is an important factor in controlling concrete quality. If the cement and/or water contents of as-delivered concrete are changed for any reason, the concrete will have different properties than what it was designed to have. While the cement content of concrete is usually well controlled during batching at ready mix plants, the water content is subject to change. Extra water may be introduced into concrete as wash water in the mixing truck or added by the truck driver as the mix stiffens. So measuring the water content of as-delivered concrete is an important quality control procedure. And the microwave oven drying method is a simple way of doing it. The method was recently modified under sharp contract for this purpose. In brief, the test procedure requires that some fresh concrete be weighed, then dried, and then weighed again. The difference between the fresh weight and the dry weight reveals the water content of the concrete. The test equipment includes a microwave oven with a power setting of 900 watts, a heat-resistant glass tray, a fiberglass cloth, a scale, a small metal scraper, and a grinding pestle. The piece of fiberglass cloth must be large enough to both cover the tray and wrap 1,500 grams of fresh concrete. Let's say that for a 9 by 9 by 2 inch tray, a 20 by 20 inch piece of cloth is needed. With all the equipment ready, a sample of concrete is obtained and the test procedure is begun. First, the fiberglass cloth is placed on the tray. Both are weighed and the scale reading is written down. Call this initial weight WI. Leaving the tray and cloth on the scale, approximately 1,500 grams of concrete are added and are wrapped completely in the cloth. The exact weight of the tray plus cloth plus fresh sample is obtained and recorded to the nearest gram. Call this the final weight, WF. The difference between WF and WI gives the exact weight of the fresh sample, recorded as WS. All weights should be measured and recorded to the nearest gram. Next, the tray is placed in the microwave. The control is set to the highest power, 900 watts. And the sample is dried for 5 minutes. After 5 minutes of drying, the tray is taken out and the sample is quickly unwrapped. With the edge of the scraper, the mass of concrete is broken until the coarse aggregate is separated from the mortar. Then, the mortar is ground with a pestle to expose more aggregate surface area. This helps the sample to dry. No more than 1 minute should be spent on the grinding, and care should be taken not to lose any material in the process. Now the sample is wrapped again and put in the microwave for another 5 minutes. At the end of the second 5 minutes, the tray is removed and the sample is unwrapped. It's stirred with a scraper, wrapped again, and then weighed. This dry weight is recorded as WD1. Next, the sample is dried again, this time for 2 minutes. Then it's weighed again. If the change in weight is less than 1 gram, the drying should be stopped, and this weight should be recorded as WD, the final dry weight of the sample. But If the weight changes more than 1 gram, the sample should be dried for yet another 2 minutes and reweighed. Then the final weight is recorded as WD. To calculate the water content per cubic yard of as-delivered concrete, the final dry weight, WD, is subtracted from the initial weight, WF. The result is divided by the weight of the fresh sample, WS, giving you the percentage of water content. Then, the percentage of water content is multiplied by the unit weight of the concrete. If the unit weight is in pounds per cubic foot, the result is the water content per cubic foot. Then, multiplying by 27 gives the total water content per cubic yard. Now notice that we use the word total when referring to the measured water content. This means that it includes the water absorbed by the sand and aggregates of the mix. Absorbed water, however, should not be considered in measuring the water content of concrete. So, what should be done? Well, since the amount of this absorbed water is provided by the concrete producer along with the mix design, it's easy to determine the actual water content by subtracting the absorbed water from the total water. In addition, with the cement content known, the actual water-to-cement ratio of the concrete can be calculated. One more important note about this test concerns the drying time. Based on the type of microwave oven shown in this program and on laboratory testing, the optimum time for drying concrete with medium to high slumps is 14 minutes. Concrete with a low slump, however, will completely dry within 12 minutes. And that's water content measurement. Next, we'll look at thermal effects evaluation. Thermal gradients, overheating of concrete, and early freezing of concrete can lead to cracking and loss of strength. Sharp has developed a guide that can be used in evaluating the likelihood of such problems arising in the placement of concrete slabs. The guide contains several tables. Using the tables requires knowing the ambient air and concrete temperatures at the job site. Measuring air and concrete temperatures was discussed in part 1 of this series. The amount and type of cement in the concrete must also be known. If pozzolans are used, the amount of cement replaced must be known too. Finally, the thickness of the concrete slab must be determined as well. All these quantities are then entered on the table, and the resultant condition is found. The table then indicates whether or not the conditions are satisfactory. There is a risk of too large a temperature gradient, there is a risk of early freezing, or there is a risk that temperatures will be too high within the slab. The guide also recommends precautions to take if thermal conditions are unsatisfactory. For instance, if the tables predict that the concrete temperature will be too high, either a cement with a lower heat of hydration or a pozzolan may be called for. And that's how the tables are used to evaluate thermal effects on concrete. Now let's move on to maturity monitoring. The strength of new concrete increases significantly with increasing curing temperature and age. In-place strength can be used as a criterion for opening bridge deck overlays, pavements, or full-depth patches to traffic. Strength development with time is typically different under laboratory isothermal and moist curing conditions than under a range of air temperatures in the field. Maturity monitoring, according to ASTM designation C1074, is used to estimate the strengths of laboratory specimens under non-standard temperature conditions. The method is based on the assumption that concrete strengths are equal if they attain the same maturity regardless of temperature history. A mix-specific strength-maturity relationship is developed using concrete that contains the same materials, aggregates, cement, and admixtures that will be used in the job mix. The use of different material sources and quantities would affect strength-maturity relationships and result in significant strength estimation errors. Two different methods of calculating concrete maturity are available. The first method is commonly referred to as time-temperature maturity. Measurement units are degree days or degree hours. The datum temperature used in calculating maturity is experimentally determined for individual mixes. It is the temperature below which the concrete does not develop strength. The second method of calculating concrete maturity is called equivalent age maturity. The equivalent age is the number of days or hours at a specified temperature required to produce a maturity value equal to the value achieved when the concrete is cured at other temperatures. For example, in hot weather, an equivalent age of 20 hours may be reached in 12 hours. In other words, the strength reached in 20 hours under the standard curing condition temperature may be reached in just 12 hours in hot weather. The value of Q, the activation energy divided by the universal gas constant, must be experimentally determined for individual mix designs. The first step of either method is to develop a strength-maturity relationship in the lab prior to construction. Temperature history is recorded using commercially available data loggers, maturity meters, or other temperature measuring devices. Thermocouples are placed in the interior of beam or cylinder specimens, and the temperatures are frequently recorded. For quicker strength developing mixes, the temperatures should be measured at 15 to 30-minute intervals. For slower strength developing mixes, the temperatures can be measured every hour until the specimens reach isothermal laboratory conditions. Specimen strength is determined at different ages. It is recommended that a minimum of 2 specimens be tested at each test interval. If flexural strength development is to be monitored from 200 to 500 psi, specimens should be tested at several ages to develop a relationship which is applicable to the strength range. At least 5 to 10 test periods are typically used to establish strength maturity relationships. The maturity for each strength test is computed, and the relationships predicting strength from maturity are established. For thin bonded overlays, a thermocouple is positioned within the plastic concrete, away from slab edges. For full depth construction and patches, several thermocouples may be positioned away from slab edges at different elevations. Usually the thermocouple wires are attached to a tree that is driven into the subbase so that the thermocouples are properly positioned prior to concrete placement. After the concrete is placed, the thermocouples sense the concrete temperatures and record the thermal history, which is used to incrementally calculate maturity. Maturity meters that directly compute maturity are commercially available. In-place slab strength is then estimated from maturity using the previously developed relationships. When thermocouple trees are used, the temperatures will vary with their depths in the concrete. Typically, the temperature near slab bottoms increases, then decreases with the cement heat of hydration at a slower rate than does the temperature near the slab surface. Maturity and strength at early ages, therefore, vary at different elevations. When evaluating traffic opening times, it is recommended that the lowest or coolest thermocouple be used, since critical load-induced flexural tensile stresses generally occur at the bottom of slabs. However, when used as a quality assurance tool, maturity is usually calculated using the overall average slab temperature. So that's what's involved in maturity monitoring. Which brings us to the end of Part 3 of Quality Control of Concrete on Site. You'll see the remaining procedures in Part 4. Here in Part 4 of Quality Control of Concrete on Site, we'll look at the last 3 procedures of the 6 new quality control tests and techniques that we began in Part 3. So first up is temperature-matched curing. Field-cured cylinders fail in many cases to reflect the actual strength of in-place concrete, especially in the early ages. Better prediction of the actual in-place strength has been needed, especially when traffic opening times for highway repair work must be determined. One effective prediction technique is the temperature-matched curing system, or TMC. TMC is based on casting the test cylinders in special insulated molds that are then maintained at the same temperature as the in-place concrete. This is automatically achieved by a heat controller that reads the in-place temperature through a temperature sensor, a thermocouple, and adjusts the temperature to match the readings. TMC equipment includes 6 4x8-inch insulated cylinder molds, a heat controller with 6 cables to connect to the molds, a thermocouple wire that extends from the in-place concrete to the controller, a connecting wire between the controller and one mold, a power supply, for example, a 1,000-watt generator, a voltage regulator or stabilizer to prevent any equipment damage from voltage changes, plastic covers for the molds, and finally, form-releasing oil, such as WD-40. In setting up the system and getting it started, the thermocouple wire coming out of the controller is first plugged into any of the molds. All the molds are plugged into the cables coming out of the controller. Then the controller is connected to the power supply through the stabilizer. All connections must be securely made to the right places. Also, each mold must be sprayed with form oil. One more thing may need to be done. The thermocouple may have to be fixed in its place prior to casting. For example, it may be attached to a steel rod or tree in the middle of the slab. The wire has to be long enough to reach the controller. All these things should be done before the concrete is received. Then, When the concrete is delivered to the site, the cylinders are cast following the standard AASHTO procedures. After the surfaces of the cylinders are finished, the molds are covered with plastic. Shower caps like these work well because they cover each mold individually. Now, if the thermocouple wasn't fixed in place before concrete placement, it should be inserted in the concrete now, after casting. Then the generator is started. The thermocouple wire coming from the structure is plugged into the controller, and the controller is turned on. During the first few minutes, the lights on the controller should be watched. Green indicates the unit is operating properly. Yellow means that the unit is in its heating mode. But flashing red means there's a problem with the thermocouple. At the end of curing time, the cylinders are demolded and made ready for testing. Demolding can be done easily by hitting the top of the mold with a rubber hammer to release the specimen. A portable compression machine can be used to test the cylinders in the field. One final note. There should be enough gasoline on hand to run the generator during the curing period. An extra container of fuel may be needed to refill the generator as necessary. That's the temperature-matched curing procedure. Next up is pulse velocity testing. As stated earlier, in-place strength can be used as a criterion to open bridge deck overlays, pavements, or full-depth patches to traffic. Again, however, strength development with time is typically different under laboratory isothermal and moist curing conditions than it is in the field while subjected to a range of air temperatures. Pulse velocity testing according to ASTM designation C597 can be used to monitor in-place concrete strength development. Pulse velocity is related to the density and modulus of elasticity of the concrete. Since strength, modulus of elasticity, and density can often be correlated, pulse velocity can be correlated with strength. Pulse velocity equipment consists of a pulse generator with time-measuring electronics, a pulse transmitting transducer, a pulse receiving transducer, and a calibration standard. A thin layer of grease or sealant is commonly applied to the transducer face to assure good acoustic coupling between it and the concrete surface. The equipment should be calibrated frequently using the standard reference bar supplied. Calibration is necessary since transit time may be influenced by transducer cable length, thickness of coupling sealant, and contact pressure. Using the zero control, the time display is set to the transit time stamped on the calibration standard. Pulse velocity is calculated by dividing the travel distance between transducers by the transit time. The electronically measured transit time is generally displayed in units of microseconds, millionths of a second. Pulse velocity is generally expressed in feet per second. For concrete, pulse velocity is commonly within the range of 12,000 to 15,000 feet per second. A mix-specific strength-velocity relationship is developed prior to construction using concrete that contains the same materials, aggregates, cement, and admixtures that will be used in the job mix. The use of different material sources and quantities generally affects strength-velocity relationships and results in significant strength estimation errors. Specimen strength is determined at different ages. It is recommended that a minimum of 2 specimens be tested at each test interval. If flexural strength development is to be monitored from 200 to 500 psi, the specimen should be tested at several ages to develop a relationship which is applicable to the strength range. From 5 to 10 test periods are typically used to establish strength-velocity relationships. The pulse velocity for each specimen is determined, and the relationships predicting strength from velocity are established. To determine pulse velocity for full-depth construction and patches, foam blocks are staked to the subbase before concrete placement. They will produce blockouts in which the pulse velocity measurements will be taken. The blocks are spaced at the same nominal distance as the specimen transit distance, since velocity at early ages can be influenced by travel path. For example, if the pulse velocity was measured on 21-inch long beam specimens and correlated to beam flexural strength, the blocks should be positioned 21 inches apart as well. Concrete is then placed around the blocks. The blocks are removed once the concrete has set enough to not be damaged. After block removal, the travel distance is measured and the transit time is measured using the pulse velocity equipment. The transducers should be positioned directly across from each other at the same elevation. The pulse velocity is computed, and the in-place slab strength is then estimated from the velocity using the relationships developed earlier. Typically, the temperature near slab bottoms increases then decreases with the cement heat of hydration more slowly than does the temperature nearer the surface. Therefore, the concrete strength may vary at different elevations. When evaluating traffic opening times, it's recommended that the velocity be determined near slab bottoms, since critical load-induced flexural tensile stresses generally occur there. But when it's used as a quality assurance tool, velocity is typically determined at mid-depth. And that's it for pulse velocity testing. Finally, we'll look at nuclear density testing. Because fresh concrete contains entrapped air when it's initially placed, consolidation by mechanical internal vibration is needed to eliminate the voids. For concrete pavements to perform well, the plastic concrete must be thoroughly consolidated. Inadequate consolidation, on the other hand, leaves the concrete weak, porous, and non-durable. Concrete may be under-consolidated in areas away from the vibrators, where the vibration energy has diminished. Consolidation problems may also occur near slab bottoms, between slip-form vibrator paths, around reinforcing steel, and around dowel bars. Quick corrective action can be taken while the concrete is still plastic, such as revibration or resetting the hydraulic vibrator frequency, magnitude, and depth. Nuclear gauges can be used to monitor the density of plastic concrete. The gauges transmit gamma radiation from a source through the concrete to a detector. The more dense the concrete, the less intense are the gamma rays reaching the detector. Monitoring concrete density with conventional nuclear gauges is discussed in ASTM designation C1040, Standard Test Methods for Density of Unhardened and Hardened Concrete in Place by Nuclear Methods. Initially, conventional gauges with single probes The kind used in monitoring soil compaction and asphalt density were used for monitoring concrete density. Those gauges, however, had their limitations, as discussed in the user's manual. To overcome the limitations, a twin-probe nuclear gauge was evaluated for field use. Indications are that commercially available twin-probe gauges, with certain required modifications by the manufacturer, work well for monitoring concrete density. The advantage of twin-probe gauges is that they can determine the density of horizontal strata of concrete by positioning the radiation detector below the pavement surface at the same elevation as the radiation source. Thus, they can detect concrete density at the bottom of the slab or under reinforcing steel or dowel bars. Conventional single-probe gauges cannot do this. The most important thing to keep in mind when working with nuclear gauges is safety. Gamma radiation is potentially harmful. Like X-rays, it can pass through solid materials. Only trained and certified personnel should operate any nuclear gauge. The user's manual contains additional safety information. Twin probe gauges must be calibrated prior to use in the field by determining the nuclear count rate of each of several materials at different and known densities. Calibration counts are determined on several hardened concrete blocks in addition to the polyethylene and 3-metal standard blocks supplied by the manufacturer. A steel calibration frame is used to hold the standard blocks and the two probes. A calibration curve is established by plotting a curve through a plot of count ratio versus each material density. Count ratio is defined as the calibration block count divided by the standard magnesium metal block count. The distance between the source and detector during the calibration process must be the same as that used for field counts. In the field before testing, the nuclear count is determined on the magnesium block. Then, the steel testing frame, mounted on a base plate, is positioned on the concrete surface where a test is to be run. The frame is used to position the aluminum guide tubes that are driven into the plastic concrete to contain the two probes. The tubes are driven to equal elevations. Next, the detector probe and the source probe are lowered into the tubes. Then, the rate meter is started, and the gamma radiation rate is counted. This count is then divided by the magnesium block count to obtain the count ratio, which is then applied to the calibration curve to determine the concrete's density in pounds per cubic foot. Since determining the concrete's actual density is not as important as evaluating its relative consolidation, a shortcut method may be used. It's explained in the user's manual. Tests can be run at different elevations to evaluate the consolidation at different depths throughout the slab and around reinforcing steel and dowel bars. Laboratory testing has indicated that the readings are influenced when the horizontal stratum is within 1 inch of steel bars. And that's it for nuclear density testing and the other new quality control tests. We've come to the end of this series of presentations on quality control of concrete on site.